ओके ओके स्ट्रीम आ रहा है ना
Please give the it's recording.
So hello everyone, am I audible? Yeah. So welcome to another course work on signal processing for millimeter wave communication for 5G and beyond. This is the assignment for week 5. So in week 4 I think there are some wrong questions like options were wrong or I have discussed like that. Probably you will get marks for all these things as I have discussed with the regular TA. So like there was a pseudo inverse case and the solution was wrong in that question, like the options were wrong, so don't worry about that. So this is week 5, so let us start from the first question. The first thing is the signal model in a communication system is described as follows, that the model is given as y is equal to hx plus w, where the input vector x is equal to as and H belongs to a complex M cross N channel matrix and A is the precoder matrix. So what is our problem? We have to estimate the transmitted signal S gap. So there are 4 methods are given here. Like the first method you can use like the mean square error, sorry, the least square error x minus mod of x square. Another thing is SVD based algorithm. Third thing is W is equal to H inverse, that is sort of 0 force equalizer, and the dth option is LMMSE estimator. So let us discuss all the things one by one. Sure. The first question, the option A, and it was like x minus x cap mod square. So how do we represent that in our this case? So actual thing is, the question is x is equal to as. So if we think about that, so this comes as a is the term that goes outside s minus s cap squared. So this is the way you can detect a signal. So option A is sort of right thing, but it is not taking any statistics. Why it is not taking statistics? Because what is our model is y is equal to some h of x plus w. So this w, for our channel model, it becomes white Gaussian noise, additive white Gaussian noise. So if we don't take the statistics of this, that is choosing the nearest vector for which x I can get this y, like y minus hx mod square. But here we are not considering any statistics of w, no term of w here. So this is the main least square solution. So this works well, and as the noise is Gaussian, this works well. Then what is the like PDF of Gaussian here? The PDF of Gaussian is like it comes like there is a mod square term by 2 sigma square. So that is the reason least square works for channel model, but it is the least square solution, but we are not taking any statistics here. So the first option is right. The second option is a SVD based algorithm. So what is the SVD based algorithm here? So the model here, the precoder is used like this. There is a precoder, and some input signal is coming here. Yes, and this precoder is A. So when the signal is passing through the precoder, it is becoming x is equal to AS, and then we are transmitting it through the channel. And in the receiver, what we are receiving? Hx plus W. So the transmitted signal is S, but what we are receiving is y is equal to Hx plus W. And now the value of precoder is giving as V, and also it said that this H matrix has a singular value decomposition, and that is equal to U sigma V star. So let us substitute this equation here. So what it becomes? Y is equal to U epsilon V star, and what is x? X is equal to AS, and this is equal to VS, as A equal to V as mentioned in the option. So we replace x as VS. So this, what is singular value decomposition? For this singular value decomposition, this matrix and this matrix are unitary matrix. So the equation becomes y is equal to, and of course the W term will be here. You cannot omit the W term. And now what it becomes? It becomes U epsilon S plus W. Why? Because V is a unitary matrix, and the definition of unitary matrix is V into V star is equal to identity matrix. So here it is the identity matrix comes. So it becomes U S plus W. So what is the solution comes here? Like y becomes U epsilon S plus W. If we use this precoder only, that is the result of the precoder. So the precoder makes this H matrix dissolved into the factor U epsilon S. Now what is the previous equation here? Y is equal to U epsilon S plus W. Now we say in the receiver end, we multiply this data Y with a unitary matrix U star. So what is U star Y? Is equal to U star U epsilon S plus U star W. So see, this U star is getting multiplied with this white Gaussian noise. And what we know, if some unitary matrix is getting multiplied with a Gaussian noise, what happens? Its power will not change. This is because the norm of the unitary matrix, that is U star U, and its trace will be like, this norm will be equal to 1, whatever the unitary matrix is there. So the noise power does not change here. But what advantage we are getting? The form term U star U, this is also unitary matrix, so it becomes epsilon s plus W tick, where W tick equal to U star W. So see, what is the advantage now? If we take this epsilon matrix and S is the actual transmitted signal, and epsilon is what? For SVD, epsilon is diagonal. So this y tick, like what is U star Y equal to, we consider at y tick, and it becomes epsilon s plus W star. So this is a diagonal element, diagonal matrix, and this is the transmitted signal. And as it is diagonal matrix, there is no multipath effect that is considerable here. Like with the help of signal processing, we are omitting the multipath effects here. Like in the sense, like for, like, let me describe it in this sense. Like this is the first antenna, two antenna are here, and two receiver antenna is also here. So this is the first part H1, and it is going to receiver end 1. This is transmitted from transmitter 1 and receiving to 2. This path I denote by H22. It's H22, this one, and this path, it is going from transmitter side to receiver end 1. So whenever we write the equation, it is y1 y2 becomes h11 h12 h21 h22, and whatever the signal I have transmitted, x1 and x2, it becomes like this, plus the noise adding up here, w1 and w2. So see, this matrix is not diagonal. So what if it becomes diagonal? h11 0 0 h22. So what the signal model becomes here for the same thing? The y1 term only depends on h11 x1 plus w1, and y2 terms only depends on h22 x2 plus w2. So see, these cross terms h12 and h21, these two terms vanish, means this two path vanishes. So that is the advantage, like you are actually transmitting through this system. But if you design a precoder, what it becomes, the system becomes like as if you are viewing the system. This is not actually happening, but this is, you are viewing with the help of signal processing. Like this, there is only one path exists and there is only one path exists, no cross term here. So that is the advantage of using the precoder based design. So option B is also correct, because it can help us to detect a signal. So the next option, option C. The option C says we just use the inversion of the channel, that is H inverse, and we try to find out what is the solution. So option C is we use W is equal to H inverse. So what happens if we use W is equal to H inverse? So what is our model? Y is equal to H x plus small w. This is noise, and this big W is the W that I'm multiplying with Y. So if I multiply this big W with Y, it becomes W H x plus W W. So what it becomes? W is equal to H inverse. So WY becomes H inverse H x plus WW x plus WW. So it is easy. See, we are directly finding what is x here, and with this noise will be always there. We cannot do anything over this noise, but this W is what? H inverse. So this H inverse into W, as I discussed earlier, in the previous case what was multiplying there? Some unitary matrix into W. So that unitary matrix is multiplying with W, does not change the power. But here it may change the power. But the biggest disadvantage is not this case. The biggest disadvantage that can happen if this H inverse does not exist. Like if H, that is NT cross NR antennas are there, and it becomes 4 cross 3 matrix, then what happens? Then inverse does not exist. So this method is the problem. So this is the incorrect statement. Option C. So and LMMSE I will derive it, but it is asking the transmitter signal which of the below method is an incorrect choice. So if I choose H inverse, it does not guarantee that our channel is as it is described M into N. H inverse exists, there is no guarantee, and it is also increasing, like it is changing the noise power if I think in that way. So it is not a perfect way. And then the last option, that is LMMSE method. So let me tell what is LMMSE method. So for the LMMSE method, what we do, it is sort of like you have a data that is Y is equal to Hx plus W. Okay, so what we do, we minimize Y minus Hx, and we take here the expectation. Only term that differs from the LS here, we are taking this expectation. So LMMSE term includes linear. Why it is linear? Because this model we are thinking Y is equal to Hx. So this is a linear model. Like it is not Y is equal to sine of H into X, that sort of thing. So we are taking a linear model here. So that is where linear terms come with the MMSE game. So what is it? It is like expected value. Let me calculate it. So expected value of mod of hx, like I can take it the first thing. It does not matters within the mod square thing. So it becomes, sorry, this is y trace of expectation of hx minus y into hx minus y transpose. This is what the definition of this. Like y, it also can be defined as this expected value of hx minus y star into hx minus y. So if I take the term trace out, this is the property of the vector algebra. Like if I take the outer product, trace of the outer product of two vectors is equal to inner product. So according to this, we can write this equal to this. So let me derive it more. So it becomes trace of expected value of hx minus y into x star h star minus y star. If we derive it and then we do minimize this factor with respect to this linear model, like the thing is, we say for LMMSE, we say that y is equal to hx plus w. So we design a equalizer, that is w, and multiply it with the receiving vector y, and we say if we do this linear transformation, it comes x. This is small w. So if I multiply this matrix w with y, it will give me the x. So that is the thing we have to minimize here. So the first condition, wy minus x and its mod square, and take the expectation over it and minimize the whole term with respect to w. So first, in the same way, we can derive this equation and minimize this, and if we derive, it becomes w comes as r yy inverse into r x and the another parameter that comes as y. So this is the two factors. Only if we know these statistics, then we can derive the MMSE. So option D is also correct here. So all the options are correct except this option C. So the right answer is option C here. So for question 2, the antenna architecture for a data transmission is given below. And the above system is an example of what? Like here is only one transmitter antenna, and the same antenna is getting boosted from the same transmitter side, but the RX side has two different boosting power amplifier. Why? It is like this. See, this side, this is the TX side, and there is two antenna here. If it was the case, then see here you can give two power amplifiers, so these two data are different, but in the question it is given like this. This is the TX side, and it comes from the same transmitter side. Sorry, this comes from the same transmitter side and giving the and transmitting the same signal. So this is the structure, it has been drawn. So if the input vector is S, it is coming here S, and it is just getting transmitted from just two things. So what is this? Single constellation, same constellation here. So this is only single input, but in the output side, this is the RX side output, and this is this. So see, the same we can receive R1 from here and R2 from here, which is not the case for here. We cannot write S1 and S2. So the right answer is SIMO, single input multiple output system. So let us go to question number 3. For beam steering in millimeter wave channel approximation, which of the following assumption is not made in general? Like the first option is antenna element distance di is greater than equal to lambda by 2, while lambda is the wavelength. So the second option is transmitter to receiver antenna distance is di, that is greater than lambda. The third option is frequency flat fading channel and single tap channel, and the fourth option is channel parameters HI are same approximately. So the first option, this assumption is made, like di should be greater than lambda by 2. Why? If di is not greater than lambda by 2, the antenna coupling thing can happen. It should be greater than the half of the wavelength. So this assumption is made, so this is not something wrong. The option B is transmitter to receiver antenna distance. This should be also greater than lambda. Like your wavelength, the transmission wavelength, RF wavelength, that cannot be lesser than the distance between transmitter side and receiver side. So this is also true, and this assumption is already made in millimeter wave. So this is not sort of something that we do not made here. And frequency flat fading and single tap channel. So frequency flat fading and single tap channel in the sense like here we are using beamforming and we are sending the signal for a particular direction. We are not changing, like there are, like with the beamforming we can think that we are transmitting for a transmitter side, and with the help of beamforming we are directly approaching to the receiver end. So if as if there is only single path, and that could be considered single tap channel, and also it is a frequency flat fading channel if there is a single tap channel, as we discussed earlier. But the channel parameters HI are approximately same. This conclusion cannot be met. This conclusion cannot be made because there would be a difference of phase shifts. Like every antenna parameter will have a little sort of phase shift. Like they are distanced by if I consider a ULA case, uniform linear array case, so they are they have a particular difference in their position, and this difference will create some sort of phase shift. So the option D is the assumption we do not make. Like we do not make the assumption that HI are approximately same. So let us go to the question number 4. Assuming the antenna element spacing d is equal to lambda, the correct expression for phase difference in antenna array manifold is given by. So this is a well-known equation. Let me derive this. So the equation of antenna array manifold this is sort of del phi I 2 pi I minus 1 d sin theta I by lambda. So what is mentioned here? D is equal to lambda. So if I substitute this here, it becomes 2 pi I minus 1 sin theta. So this is the right answer. So the option is option B. Option B is the right answer here. So let us move to the next question. This is question number 5. It is said a uniform linear array in communication system contains. So it is well known that if it is a uniform linear array, the first option is n element placed at equidistance and signal is transmitted of non-equal magnitude and progressive phase shift. So if it is uniform linear array and it is just providing a progressive phase shift, but the magnitude it will be equal for all of them. And this phase shift comes why? This phase shift comes because if these are the antenna elements and they are getting fit from this is the electric signal coming here and there is a difference only. This difference is D. So the difference will be with a progressive phase shift. But it has nothing to do with the amplitude. This amplitude E is not attenuating. Only it is giving the phase shift because there is a difference of D between these 2 points. So correct option is n elements at equidistant signal is transmitted of equal magnitude and progressive phase shift. So option B is the correct answer here. So the next question is, suppose in a communication system the receiver has a ULA means uniform linear array antenna with 3 antenna elements at the receiver and 1 transmitting antenna. The angle of arrival AOA at ULA is pi by 3 radian, and most important line is here measured vertically with respect to the ULA antennas. So assume that antenna spacing in ULA is d is equal to lambda by 2. So what the steering vector takes? which form this steering vector takes. So let us derive this equation once again. So theta, angle of arrival, that is pi by 3, but it is vertically. So we know that phi I, that is a difference. This is 2 pi I minus 1 d sine theta I, and by what? By lambda. Lambda is the wavelength here. So here, what is theta? This is pi by 3, but this is vertically. So theta I will be pi by 2 minus pi by 3, pi by 6. So if we substitute I is equal to 1, 2, 3, for I is equal to 1, what this phi becomes? This I equal to 1 minus 1, 0. So this becomes 0. Delta phi I, phi 1. Similarly, if we substitute I equal to 2, it becomes 2 pi lambda by 2 by 2, as d equal to given lambda by 2 in the question, and it becomes sine pi by 6. Cancels out 2 2. So term remains is pi by 2, and this is phi 2. Similarly, if we put phi 3 becomes pi. So what will be the steering vector type of thing? It is e to the power j phi 1, e to the power j phi 2, e to the power j phi 3. So if we substitute, this is 0, so it becomes 1, e to the power j, substitute this phi 2, this becomes pi by 2, and it becomes e to the power j. So option A is the correct answer. J pi by 2 and j pi. So steering vector takes this form. So let us move to the question number 7. So here it is given the transmitter and receiver manifold vectors in simple communication setup are given by a to the power t is equal to 1 e to the power j 0.1 and a are equal to 1 e to the power minus j 0.1. And we also can think the attenuation factor. This attenuation factor can come from the phase equation or anything, like it is only giving the attenuation. And the steering vector is because there are multiple antenna manifolds. So the phase is coming like as I discussed in the previous question, like e to the power j del theta, that term is giving the second term, rise to the second term. So it is asked what is the trace of the channel matrix becomes. So let us first derive what is the channel matrix here, and if we can derive the channel matrix, we can say what is the trace of this channel matrix. So the question number 7, that is there are HT number of transmitting antenna and this is a bulk of receiving antennas. So the transmitter matrix, it will be alpha AR bar to AT bar transpose. So it is giving alpha is equal to 0.5 and AR is equal to 1 e to the power minus j 0.1, and this is 1 e to the power j 0.1, as it is a transpose factor is here. So this becomes 0.5 and the matrix is 1 e to the power j 0.1 e to the power minus j 0.1, and the last term here it becomes 1. So trace, what is trace of this matrix? 0.5 into trace of this matrix, 1 e to the power j 0.1 e to the power minus j 0.1 and 1. So it becomes equal to 0.5 into 1 plus 1, and this is 1. 1 is the correct answer. So the correct answer is option C. Answer is 1. So the next question, that is, here is a rotation matrix of steering a beam angle of 30 degree for a data vector. So rotation matrix is given by beam angle of 30 degree, and we have to derive what should be the rotation matrix. So the main task here, we have to know what is the rotation matrix and how it works. So here let us think there is two vectors v and v dash. This angle is theta and this angle is theta plus phi. Okay, so what is this angle? Phi. So our statement is we are moving this vector v by an angle of phi and it is becoming v dash. So we can say there is a matrix H which is getting multiplied with v and it becomes v dash. So this H is the rotation matrix. So first us derive what is v in terms of regular bases. So I can say it has a x component and y component. So for this vector v, this x component is v cos theta and it is v sin theta, and for this vector v dash is v dash cos theta plus phi, and this is like this magnitude will be same. I am only rotating the vector, so it will be the same. The angle will be different only, and this is v sin theta plus phi. So what is v cos theta plus phi? This is equal to, so we can write v dash. Let us write v dash. What is v dash in terms of vector? V dash, and I write a vector here. The first term is the x component and the second term is the y component. So this is cos theta cos phi minus sin theta sin phi, and a term v is multiplied with it. So v cos theta v cos phi, v sin theta v sin phi. What, from where it comes? Like if we derive this, the first term x component is this, and what is the second component? Is sin theta cos phi minus, sorry, this term, this comes here, cos theta sin phi. So we multiply h with a matrix, this v cos theta and v sin theta. This is v, this is h, and it becomes this v dash, v dash. So see, if we substitute the values here, like it becomes cos theta, it becomes minus sin theta, it becomes sin theta, and it is cos theta. So what it becomes? The first term v cos theta cos, sorry, this is phi, 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 phi. These are phi, not theta. So this becomes v dash, like multiply the first two term, is cos theta cos phi, v cos theta cos phi, and if I multiply the second term, it becomes like sin v sin theta sin phi. So from here, what is the conclusion? Conclusion is the rotation matrix, it takes the form like cos theta minus sin theta sin theta cos theta, if I want to move by angle of theta. If I represent that is term of phi, as we have derived in our equation, it should be cos phi minus sin phi cos phi. So it purely depends on the angle theta by which you want to rotate. So if we rotate by theta equal to 30 degree, what it becomes? It becomes cos 30 degree minus sin 30 degree sin 30 degree and cos 30 degree. So it becomes like the first term becomes minus 0.8, sorry, 0.86, and this is minus sin 30 degree, so it becomes minus 0.5. This is 0.5 and this is 0.86. So the right answer is option A. This is the right answer. So the next question is question number 9. It is given that a data model is given y is equal to hx, and we have to derive what is the zero force equalizer h inverse here. Show. Question number 9 is it, and what is given? Y is equal to hx, and h is given as 0.95 0 0 0.9. So what is h inverse? If h is a diagonal matrix, then its h inverse is just 1 by 0.95, 0, 0, 1 by 0.9. What is this? Just the reciprocal of diagonal elements. So the whole thing becomes 1.05, 0, 0, 1.11. This is the right answer. So the right answer is here will be option number B. And the last question, the uniform linear array has its maximum radiation for the angle of. So if it is a uniform linear array, as I taught in the lectures, the maximum radiation will happen at the angle of 90 degrees. So that is common in the, like, you can follow up the lectures, and if you need more discussions, I will discuss in the next class if you have any doubt about this. So this is for today's class. So any of you have any query about whatever I have discussed till now? Yes, 10th one, right? The 10th one is 90 degree. It is okay. Okay, I think nobody has no query here, so we can leave this meeting here. We'll meet in the next Tuesday.